Yeah.
So this is our compound machine project. It's by me and Sean, and our firm is Mining Intrinsically Neat Extraction, or MINE, and the total cost was $742,000, or 0.742 kilograms.
So this was our design brief. Our client was Steel Extraction LLC. Our target customer owner of mining companies, because this is obviously extracting steel from mines. So we just found a way to move the steel up 12 inches in under 30 seconds. Obviously this was a two-week maximum, 3 simple machines, under $3 million, which is $1 million equals 1 kilogram of mass. And then must have at least a minimum AMA of 3. And then again, the 1 kilogram mass must be lifted 12 inches in under 30 seconds.
Here are some of our brainstorming sketches. You can see that we have one from the side view here. You can see both gears in action. And then we originally were planning on having a inclined plane, but this wasn't working well for our AMA, and it was difficult to try to balance. So then we moved into our current final prototype, which involves a pulley rather than this inclined plane. And here you can see this obviously reflects much of what's in that because it was our sketch for this design.
Man, that's an intense sketch there. That is nice.
So this was our decision matrix. We did this before we started designing. So originally we had the inclined plane, and we had a lever here that we would use with like a pulley and a gear, and we'd pull the lever down and lift it up. But we decided that that would not be as efficient or as good if we did a third-class lever. So we decided we'd use gears and pulleys this way, standing up straight this way, and then an inclined plane down this way. But then we changed from the inclined plane while we were designing because it was too much mass and not very efficient.
Here are some photos of our machine. So you can see all of the different simple machines here. Because at the start we have the wheel and axle here, which helps with our input. And then you can see that's here on the machine. And then we have our compound gears. It's just a gear train. You can see it goes vertically and helps transition the movement from the input to the output. Here's the top of our block and tackle. You can see the pulley goes down and it connects into here. And then on the bottom of it, it just reflects these two. It has 2 input strings going up and 2 strings going up from that. And so that's kind of reflects down by where the weight is, so that just pulls it up that way. You can see here that it goes about 15 inches, which is slightly more than the design required. Here we have all of our calculations. So our resistance force was 1 kilogram, and then gravity, so that was a total of 9.81 newtons. The effort force was roughly 2.4 newtons when we measured it with a force meter. So this leaves our actual mechanical advantage to be 9.81 divided by 2.4, which is about 3.8 for our actual mechanical advantage, which is over the requirement of 3. And then our ideal mechanical advantage for the first wheel and axle, as like this wheel and axle, was a 0.3 because it went from a larger to a smaller. And then our gear ratio from the vertical gear train was 1.4. And our IMA of the second wheel and axle was 4.67 because it greatly decreased in diameter. And then our ideal mechanical advantage of the pulley was 5, as there are 5 strings coming up from the pulley in which the weight is on, which leaves our total ideal mechanical advantage to be about 9.81, and our efficiency would be around 39% with this design.
That's the end of our presentation. Then we can show you how it works.
All right.
So, use.
All right. Very good. Nice job. All right. Who's next?